Okay. All right. Yeah. So far, we've talked about a lot of stuff. So we started with the autoencoder, then the VAE, GAN, convnets, word embeddings, then RNN, and last also sequence to sequence. So now we're we're gonna mix the two, which are CN. So we're gonna mix some of the stuff: CNN, RNN, and GAN. So the topic of today is image to text, but it's a rather short one. So hopefully we can actually end this session maybe before an hour and a half for the first time. Right. Okay. So the topics are image to text, or what is called image captioning. And there are very, very famous tool works regarding this domain, which are show and tell, which is the very first neural image captioning work, and then show, attend, and tell, which actually adds attention mechanism on top of show and tell. Then there's text to image. So text to image is conditional generation of image. So given a text, you generate image. So it's the other way around. Image to text is given an image, you generate a text describing the image, and text to image is given a text, you generate an image, and that's when we mix RNN and GAN actually. So we've already covered a lot of the basic components, so I hope that this is not going to be too difficult for you. So image captioning. So image captioning is just as a reminder, we sequence to sequence was text in and text out. So translating French to English, something like that. So basically, translation is one of the very representative example of sequence to sequence, and image to sequence is now a image in and text out. So it's describing a given image in text, or what is called image captioning. Still, it's an very ongoing, a hot topic. It's an ongoing task, especially with the VQA stuff going on these days. All right, image captioning. So these are the very basic examples. Note that these are all machine generated. So given an image, these texts are all generated by machine. So a person riding a motorcycle on a dirt road, or a group of young people playing a game of frisbee, a herd of elephants walking across a dry grass field. All three are very accurate. So you can see that the machines can do a pretty good job of image captioning. And when this first came out, it was like mind blowing. It was like, I mean, people were doing this even before. Image captioning it has some history. So it's not like people started to realize they can do this after the deep learning era in 2014. People were doing this even before that, but it's the meaning of the whole like neural image captioning is actually, we'll talk about this after this session. So yeah, so image captioning or image to text is still using encoder decoder architecture. So sequence to sequence was you encode the sequence with an RNN and you decode the sequence, you output a sequence or generate a sequence with an RNN. And if it's image to sequence, then obviously the encoding would be CNN and decoder would be RNN. So you're just changing the components now. So that's what basically what deep learning is about these days. You just have a lot of like basic functions, and you want to mix and match them together so that you can do like a really complex task, such as like conversation chatbots or image captioning or VQA or that kind of stuff. All right, so we'll move on to show and tell. Show and tell was I think, yeah, it was published. It was presented in CVPR 2015. So it's a neural image caption generator. So back then it was called NIC. And why this paper is important is because it's the first paper to perform image captioning without any domain knowledge. So before that, people used to do like object detection first and then generating text to describe the objects, or they would heavily rely on language modeling, or there would be like description templates. So people with linguistic knowledge would prepare a set of templates, like subject is doing or subject is giving object to like another object, something like that, like some templates, and then by using a classification you select the template and then you fill in the template with the objects that you detected, something like that. And but here this show and tell doesn't rely on any of those things, so there's no pre-processing or there's no templates or linguistic language modeling. It's just a pair of images and its descriptions as a training data, and then you just train it and then the model can do it. So which really emphasizes the flexibility and the potential of neural networks. And so this is not ranking. There was also a ranking. So given an image, what is the like the text that is most relevant to the image, and you would do that by like sorting the relevancy of the text. So you have like a set of like bunch of text, like maybe 10,000 or 100,000 sentences, and then given an image, you need to select the one that is the closest. So that is ranking, like image retrieval or text retrieval or search engine. But here, show and tell is pure generation. So it's not like there are already sentences given to you as a repository. You generate from nothing. So basically, it's another form of translation, I guess. You translate image into a text. And yeah, it enables end-to-end training. So there's not like any component that you need to pre-train or nothing like that. Actually, no, there is a pre-training going on, but still, it's not like this like a complex like sampling and inference and stuff. It's just, you just do back propagation from top to bottom. So the architecture is super simple. I mean, now that we've learned a lot of stuff so far, like we've all covered the basics, the basic components of modern deep learning, which are like CNN, RNN, and autoencoder and GAN and stuff. So now that we know that stuff, it's very easy to understand what's going on here, or hopefully it's easy for you guys to understand what's going on here. So the architecture is just, you connect CNN output with an RNN input, and that's it. So there's an image, input image goes into the RNN, to the CNN, to the convolution, and then the convolution will generate some kind of representation vector, and then the vector will go into the RNN somehow, and then the RNN will generate this form, this kind of a caption. Yeah. A bit more detailed architecture is, this is like the very first attempt at neural image captioning. So it might look a bit weird architecturally. Like some of the choices were a bit, I guess, unconventional. I mean, this is the first time trying this, so that it's not like there was like convention before this. But yeah, when I first read this paper, I thought it was a bit strange, because what's happening here is the image is given to some convolution. So this is a convolution, and actually, let me just. Yeah, this is the image encoder, and it doesn't say in the paper, but I think it is Inception version 1. It's because this architecture was borrowed from the very first batch norm paper. So batch normalization. We already talked about batch normalization, and that paper already was introducing some new architecture. And I think it is Inception version 1, because the batch normalization came from Google, guys, and Google made Inception like version 1, version 2, version 3, and version 4. So probably, and by the looks of this architecture, there's like a lot of components repeated, and so it's probably Inception then. Yeah, so this is Inception, and the text decoder is LSTM. Oh yeah, and the one caveat is the Inception version 1, Inception that is pre-trained on ImageNet. So it's already seen a lot of images, and it performed a lot of like 1,000 way classification. But that's probably for like squeezing out extra performances. But I'm not sure if this is like absolutely necessary. If you have enough number of training samples in your text image captioning, then you probably don't need to rely too heavily on pre-training. But anyway, the important message is that the image encoder and text decoder could be anything. It doesn't have to be Inception. It doesn't have to be LSTM. Text decoder could as well be GRU, because GRU is as powerful as LSTM. And image encoder, you can use ResNet or whatever. It doesn't really matter. And the architecture, so as you can see here, there's a decoder, and the output of the image encoder is fed into the decoder. So it's not like you initialize the initial vector of the LSTM as the output of the encoder. You actually explicitly put the encoder output as the input to the decoder, which is a bit weird in my estimation. Yeah, because people, if you think about the sequence to sequence translation, what they did is, so there's LSTM encoding maybe French, so there's like French words, and then you use this as the okay. So I'm gonna say this is H H H H. So this is H4 H1, and then this is S0 S1 S2, so on and so forth. And then you put start symbol here, start. Then you just start generating the first word, and then the second word, like this. And so what I'm trying to say is, before in the sequence translation, the final representation, or the hidden layer, so this one, the representation vector for the French sentence is used as the initial vector of the decoder. Because usually what people do with initial vector is just set them to 0. But instead of setting them to 0, what they did is they use the output or the hidden vector of the encoder as the initial vector of the decoder. But here we're not doing that. We're actually explicitly feeding the output of the image encoder as the input to the decoder. And then after that, you start feeding the start symbol, start, and like there is an apple or whatever on the table, and then end of sentence, EOS. So it means that the words and the image lives in the same latent space, because they are all equal. They're all equally fed into the LSTM. So, well, actually, yeah. So this, we'll talk about the technical detail later. All right. So anyway, so yeah, that's the kind of the approach that these guys took when they were presenting show and tell for the first time. But the detailed architecture is super simple. So it's just, I think it is even simpler than sequence to sequence, now that you think about it. So each SI is predicted based on PI, and SI is the word. So it's just different notations. SI is actually the word itself. So SI could be like S0 being start, as written here, S0 being start, the final one being end, and S1 would be the actual word, like there. S2 being is, and then the P is so SI is predicted based on P. So let's start from the top to the top down. So there's a log probability of a certain word. So that word is predicted based on P. So it's a softmax on top of P, and then each P is derived based on Pi minus 1, Si minus 1. So P, you can think of P as the hidden vector of LSTM. It is not exactly hidden vector of LSTM, because they slightly change in the show and tell paper. They slightly changed the equation of LSTM, but you can just basically think of the PI as the hidden vector of LSTM. So hidden vector of LSTM, usually noted H, is now it is denoted as P. So that's the difference. All right, there's a question. 네. 각각이 각각 그냥 맞습니다. 그냥 LSTM을 썼다는 걸 강조하기 위해서 그렇게 한 거고 사실 이제 H1, H2, H3을 P1, P2, P3이라고 보시면 됩니다. 네, 그럼 넘어가겠습니다. 네, 그래서 okay, so you can just think of P as an H, and so so RNN, so this is LSTM actually, LSTM. It receives the previous hidden layer or previous hidden vector along with the current input, and it generates. Actually, I'm sorry about this. This should be. Oh no, I'm sorry. Yeah. So yeah, the previous word, because this is actually like auto-regressive language modeling, because you're generating based on your output, your previous output. So what you feed in your whatever you predicted into the next one. Of course, when you're training, you just give the ground truth here, but when you're actually on the test phase, or when you're testing the model, or when you're doing inferencing, you need to predict your word, and then feed it to predict your word, feed it to the next one, predict your word, feed it to the next one. So yeah, so your current HI hidden layer would be based on your previous hidden layer and your previous output combined with a word embedding vector. So there's like a word embedding matrix. So you just don't put. So usually S1 is represented as a one hot vector. So there's like a lot of like dimensions, and only one of them will be one. All the others will be zero. This will be the same with here. Like a lot of like maybe this is the only one, and all the others are like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And you want to convert it to a compact representation. Maybe so this would be like 100,000 dimensional, 100,000 D, but you want to compact it into 512 dimensions. And the way you do it is you just multiply with a word embedding vector. So this word embedding vector, word embedding matrix, and this matrix would have the dimensionality of 100,000 dimension by 100,000 by 512. So it's like a really vertically really long matrix. So that's the word embedding matrix. And the interesting part is S minus 1, which is supposed to be the word that is given before the start token, is the output of the CNN. So it's the encoded, image encoding or image representation vector. So supposedly, everything is embedded into 512 dimensions. So the image of the representation vector of the image, the words, the RNN hidden layers, everything is just 512 dimensions. And so how they do it is there is some output from the image encoder. Supposedly, it is supposed to be 512 dimensions output. So you put a 128 by 128 image, you put it into the image encoder, then you will obtain a 512 dimensional flat vector. Question from Chegin Kim. 지금 이게 그 그림이 약간 헷갈리게 그려놔서 그런데 이 저자들이 히든 벡터랑 아웃풋 벡터를 혼용을 해서 씁니다. 이제 그러니까 LSTM 그러니까 RNN 자체는 원래 아웃풋을 우리가 달아주는 대로 생기는 거기 때문에, 그러니까 각 타임 스텝마다 원래 나오는 건 히든 벡터가 나오는 거고, 그 위에다가 이제 소프트맥스를 달면은 히든 벡터가 이제 어떤 그 프리딕션으로 바뀌게 되는 건데, 기본적으로 LSTM은 이제 시퀀스를 넣고 그 시퀀스 개수만큼의 히든 벡터가 생성되는 시퀀스 인코더라고 보시면 됩니다. 그래서 여기서 일부러 그렇게 그걸 강조하기 위해서 이제 LSTM에서 히든 벡터들이 나온다고 이렇게 말을 한 건데, 사실상 이제 그림이 약간 좀 헷갈리게 돼 있긴 합니다. 자세한 거는 그 페이퍼를 읽어보시면 알게 되실 거예요. 왜냐면 LSTM이 정확하게 LSTM이 아니라 얘들이 좀 나름대로 튜닝을 이렇게 좀 수식을 바꿨기 때문에. All right. Okay, so moving on. So As I said, output of CNN is also 512 dimensional. So everything is 512 dimensional. Your word embedding, your image encoding, it's all 512 dimensional, meaning that they live in the same 512 dimensional space. And then the image embedding is fed into LSTM at time -1. So that is the trick, how they inject the image information into the decoder. So how they inject that information is actually feeding the image encoding into the LSTM like an input. So not used to initialize the LSTM hidden vector. So I haven't seen the detail there, but hidden layers of the hidden layers of LSTM are probably initialized to 0 because there's nothing else to rely on to initialize your vectors. And and the pre-trained word embeddings didn't help much. That was the interesting part. So they pre-trained the image encoding with an ImageNet. They also tried to pre-train this one, this WE, with word2vec, and they say it didn't help that much. It didn't help much. So, and they used beam search, which the size of beam was 20. So I don't recall describing in detail what beam search is, but basically it's just trying to generate a candidate of text from your decoder. So usually once you've trained your decoder, what you usually do is there are basically 3 simple ways to generate a sentence with your trained decoder. One is you feed the start symbol, and then you have a softmax alpha probability. Like there are like 100,000, like several thousands of words, candidate words, and your softmax will indicate which one is the most likely word or the most probable word, and you select that. It's like greedy deterministic decoding. So you select that, you feed it into the next word, you select the maximum probability word, select that, and then you feed it to the next word. So that is like the greedy deterministic decoding. So that's one way to do it. Another way is simply just sampling based on this multinomial distribution. So this is output of the softmax is multinomial distribution, multinomial probability. So you can actually sample from that and then feed whatever is sampled from here, you feed it to the next one, and then you sample here again, feed it to the next one. So that is stochastic decoding because you're sampling every time step. And beam search is kind of the other ways. Beam search is you set the size of the beam, which is here in this case 20, and then you select the 20 most likely sequence. So you keep a candidate, 20 candidates that are most that has the achieve the highest score so far. So when you're in the step 1, you select the top 20 words, and then you feed it to the next, and then you select another top, and then you feed those 20 words into the next step, and then you will have some like probabilities again, and then you select whatever maximizes the probability of the 2-word sequence, because you have one word here, you have another word here. So I mean, you have a 1-word distribution here, another 2nd-word distribution here. So you're given 2-step choices, and then you select like top 20 based on these 2 distributions. So if you select like one here plus so like W1 plus W2 must be like some score. So you select that one, and then you select another pair of words and select that score, and you do that until you fill in the top 20 candidates. So as you move on time step to another time step, you dynamically like erase or add or remove the sequence from your beam pool, and finally you're left with 20 most likely sentence candidates. So that's basically beam search, and yeah, they use beam size 20, and then yeah, it's trained with not negative log likelihood. So you start. So let me just erase all this. So yeah, you have the image in, you have the ground truth in. So this is ground truth. We're talking about training phase. You're given the image, and then you have the ground truth sentence or words, and then you have the y hat y hat, all the way to y hat. So you basically just do just backpropagation, just the same style as you did with sequence to sequence translation. You just do backpropagation on all these loss terms. So there's like a loss term, negative log likelihood loss term for y1 hat and y1, plus negative log likelihood loss term for y2 hat, y2, so on and so forth. And then everything will be trained end to end. The entire LSTM, the word embeddings, the image encoder CNN, they will all be trained end to end from simple backpropagation. So so the question, are the embeddings normalized? I'm not sure which embedding you're talking about. The image input would be probably normalized to like pixel values between 0 and 1 or -1 and 1. The word embeddings, I'm not sure if they're like, what you mean by normalizing the word embeddings? Usually you don't normalize the word embeddings. Like the output of this layer is just some vector, and you don't normalize them explicitly. 512로 맞춰 넣으려면 어떤 값이든 W가 필요할 것 같은데. 어떤 값이든? 200이 아니라면 어떤 값들로? 그냥 random initialize 하는 겁니다. WE. So WE, the embedding matrix, is randomly initialized. And as I said, its dimensionality is 512 on the output side and the vocab size of your vocabulary on the input side. So that's your matrix. And you just randomly initialize it, and then you learn its parameters by backpropagation. 소프트박스 샘플링하는 이유는 그냥 스토캐스티시를 원하는 겁니다. 그래서 샘플링을 했을 때 최고의 단어를 고르면은 이제 너무 그리디하게 디코딩 되기 때문에 그냥 어떤 그러니까 똑같은 LSTM에서 맨날 항상 최고 확률을 고르면 항상 똑같은 그 센텐스가 나오니까 그게 싫어가지고 여러 개를 샘플링 해보려고 샘플링을 하는 거예요. 오케이, 네. The output of CNN, 전지수님, the output of CNN이 뭐 어떤 질문이시죠? Are the embeddings normalized? Output of CNN? No. Output of CNN is not normalized. Only the input image is normalized. All right, moving on. So this is the end of show and tell, the whole architecture. As I said, I consider this even simpler than sequence to sequence. So by looking at this, I hope everyone can actually implement this in PyTorch. Just all you need is this. All you need is these equations to implement this show and tell, right? All right. Yes. So a bit of a performance, because we're going to move on to show attend and tell, and we're going to compare the performance between show and tell and show attend and tell. So let's just talk about a bit of the experiment side. We usually don't do this though. So popular data sets for image captioning are the most frequently used one is MS Coco these days, if I'm correct. But there are a couple more. So there's Pascal Voc, Flickr dataset. I'm not sure what SBU is. Yeah, I'm not really sure what this is. I'm not a image captioning guy, but Flickr is a internet-based service. Like it's a photo service. So you can upload whatever images that whatever photographs you've taken to the website Flickr, and they will somehow manage it for you. It's like Google Photo it's like way before Instagram. It's just like a photograph service. I'm not sure if it's still there though. So yeah, during our practice session, we'll be using Flickr 8K, which is like the smallest data set. Among like MS Coco is like hundreds of thousands of images. Flickr 8K, probably only 8,000 images. 8,000 images. 6,000 training, 1,000 validation test set. All right. Okay. So this is still kind of a translation test. So the output or the captions are measured by the same measure or same evaluation metric used in the translation task. So we use like the blue score. Here it's blue 4, Meteor, Cider. They're all like translation evaluation metric, and compared to like even better than humans, actually even better than humans. So when the performance was measured with blue 4 score, humans achieved 21.7. Neural image capturing show and tell achieved 27.7 for MS Coco, the largest data set, which is pretty impressive. And on other data sets, still like near human performance, especially for like Flickr 30K. Humans achieve 68. This is blue. Yeah, this is blue 1 score. So humans achieve 68 points. And I see neural image capture 66 points. So this is already like the state of the art performance. But then again, there's no like real. I mean, there are a million different ways to describe a given image. So it's not like humans are qualitatively or quantitatively worse than machines, because there's not like it's not like we're solving a mathematical equation. It's like this is a domain of creativity. Like how you want to describe a given image, it's up to you. So there's no fixed answer. And obviously, this blue 4 score or blue 1 score, this was measured against the ground truth image captions. And actually, I think in MS Coco, there are 5 captions per image. So because it was all human annotated with maybe an Amazon Mechanical Turk or something. So a single image comes with 5 different captions. Maybe it was 4 captions or 5 captions. The details I forgot, but it's not like there's only one caption per image. There are 5 ground truth, 5 captions per image. Maybe it's the same with Flickr. I'm not sure. I've never looked at the Flickr dataset myself. All right. So yeah, moving on. So yeah, some evaluation results. So this column is the ones that the human evaluators deemed good, and this one's like kind of okay. This one's not okay. This one's totally weird. So, and yeah, these examples were the ones that you've seen in the first page. And yeah, if you take a look at these, there's something off in individual examples. So it says that 2 dogs play in the grass, but there are 3 dogs actually. Oh, it says my internet connection is unstable. All right. Can everybody hear me? Okay, yeah. Okay, cool. All right, moving on. So yeah, there are 3 dogs. I'm sorry. There are 3 dogs, but it says 2 dogs play in the grass. So it's like partially true. 2 hockey players are fighting over the puck. So there are 2 hockey players, but you don't see a puck. So you actually don't know what they're doing. It's just this model is imagining things. So we can't really say for sure if it's correct or incorrect. And this one, a close-up of a cat laying on a couch. Well, first of all, this doesn't look like a couch. This looks like a bed. And it's not laying. Laying is actually it's a transitive verb. So it should be lying. So it should be lying. So yeah, close-up of a cat lying on a couch. So first of all, it's not a couch, it's a bed. And I don't think it's lying on the bed. It is sitting on the bed. So yeah, again, like partially true. Looking at the third one, a skateboarder does a trick on a ramp. So there is a ramp, but this guy is not a skateboarder. This is a biker. So a biker is doing a trick. So that is clearly a wrong caption. A little girl in a pink hat is blowing bubbles. So there is she looks like a girl. She has a hat on. She's not blowing bubbles. So that, again, like clearly a wrong element in the caption. And red motorcycle parked on the side of the road. This is not red. This is pink. So I guess that's the clearly wrong part. And we move on to the final column. A dog is jumping to catch a frisbee. So I'm not sure. Yeah, there is a dog, but the dog is not jumping, nor is it catching a frisbee. So that's clearly wrong. Refrigerator filled with lots of food and drinks. So yeah, this is not a refrigerator. So that is clearly a wrong caption. I mean, it does look like, from far away, it does look like a half open refrigerator with its like white exterior and a lot of like junk here. So I guess it could be, you know, misconstrued as a refrigerator. And the yellow school bus parked in a parking lot. So it is yellow. It looks like a parking lot, but it's not school bus. It's a weird car. So yeah, yeah, it's not like all of them are bad. So some of them are there. Yeah, like there's not a single miss here. There's a bit of a missing or incorrect or imagining elements, and then as you move on to this direction, there's like the degree of mistake is getting like, you know, big. It's just more mistake and more mistake basically. But still, it's not like they're all like, you know, legitimate sentences. It's not like, you know, weird word jumble of words. They're all proper sentences. It's just that the contents is a bit off. All right, moving on. I mean, it's still like a very impressive result, because all you gave to the model is just pair of image and its ground truth caption, and it can actually just, you know, start generating captions for images that it has never seen before. So this is probably images that the model has never seen before. This is all test images, so it's all zero shot, and it is doing quite a good job in my estimation. All right, moving on to show, attend, and tell. So this paper was from almost the same set of people. So again, yeah, a bit of mix from the Google people and University of Montreal, I think. So show, attend, and tell. So it's mixing attention mechanism with image captioning. That's it. So that's just, you have the show, you have the show and tell, and then you just add the attention mechanism on top of it. This was presented in ICML 2015. So this is all like very long time ago. All the architectures and techniques that we are learning in this class are really like, you know, by today's standards, like old classical deep learning architecture, except for the ones that we're going to learn in the last two sessions. The basic the workflow is, of course, there's an image, and then you put it into the convnet. Again, you need to encode the image somehow, and the convnet will spit out a 14 by 14 feature map. So 14 by 14 feature map, and then you somehow use the you have the RNN with attention. So RNN plus attention over the image. So the attention will be applied on top of this 14 by 14 feature map. And then based on that, the RNN will spit out a sequence of words. It's 14 by 14. Yeah, 14 by 14 is actually, yeah, that's a good question. We'll get into that. But just to give you the answer, like the spoiler, the 14 by 14 is basically just 14 by 14. And then there's like a bunch of, so it's a tensor. So this is like the number of channels. Number of channel. So you start encoding. You start the doing convolution operations on top of your image, and then it becomes like it becomes smaller and smaller. You start with like a 128 by 128, and then after several layers or several operations of convolution, your hidden layer or your hidden representation becomes smaller and smaller. But I mean, the height and width becomes smaller, but your channel grows larger and larger. So at some point, it'll be 14 by 14 by number of channel. You take this, and then you apply attention over this. So basically, that's it. All right. So just to give you a bit more interesting examples. What the model can do is now, so given an input image like this, so this is an input, and the example is a bird flying over a body of water, and so that is the output caption. And the top row, this one is soft attention. So there are two attention mechanisms this paper uses. One is soft attention and another is hard attention. And the performance difference between the two is like very like negligible, and it's way easier to implement and train soft attention, which is the attention mechanism that we learned in the previous session. So we're not going to deal with hard attention because hard attention requires like reinforcement learning techniques to actually train this. So it's not very stable. So we're going to only talk about soft attention. Hard attention is the output of the hard attention is this. But basically what is important is as the generator or the decoder is generating the word one word at a time, it is attending to different parts of the image. So a bird, it's like a bird flying over a body of water. Like the RNN is generating this word one at a time. And when it's time to generate the word bird, it is attending to the bird portion of the image. And when it is time to generate water, it is attending to everything else but the bird. So, you can actually see what's going on. You can actually see where the model is attending to when it is generating its output word. So it's pretty, very similar to sequence with attention mechanism. When you are translating French to English or English to French, you could actually see which part or which part of the input sentence the decoder is attending to when it was time to generate like word at time step 2 or time step 3, time step 4. So it's very it's very similar in spirit. Yeah, so it's just as a reminder, sequence to sequence with attention, the architecture was like this. So you have the input encoder, and the encoder's job is done. And then once you have the H1, 2, 3, 4, you mix and match these together via attention mechanism every single time you generate one word at each time step. So this is the t equals 2. So this time is time to predict y2. And when it's time to predict y2, you first need the context vector c2. And then in order to generate context vector c2, you use s1 and all these. And all these would be pulled together using attention mechanism. And then so basically you did a pair. So s1 comma h1, there's a function, attention function, and there's f attention function, s1 h2, f attention function, s1 h3, f attention, s1 h4, and then you do a softmax on all of them, 1, 2, 3, 4, and then you get the convex weight, and then you mix and match the h's to get the c, and then given the c, s1, your previous output y1, you can generate at your s2 via LSTM, and then you can predict your y2. So that was sequence to sequence with attention. In the same spirit, what we need an encoder to obtain image representation. We need a decoder to calculate the caption. So obviously these would be CNN and RNN. So this would be CNN, some RNN, and attention module to calculate the attention weights. So the choice of architecture in this paper was for the image encoder, they used Oxford VGGNet. So we briefly talked about VGGNet. The VGGNet sits between AlexNet and InceptionNet, if I'm correct. AlexNet. I think there was one more. Anyway, so historically VGGNet was proposed back in I'm not sure, 14 or 15. So it's Anyway, so their choice of architecture was VGGNet, and the decoder was LSTM. And of course, for attention module, they just use simple MLP. So for attention function, for predicting a scalar value between negative infinity and positive infinity, they just use a simple MLP with hidden layers and stuff. So before we go dive into the technical details or the equations, just as a reminder, you need to think of the convolution operations. So given a image of 32 by 32 by 3 channels, RGB channels, if you do convnets, using 5 by 5 by 3 filters, then what you get is, I mean, six filters of 5 by 5 by 3, then your height and width being 32 and 32, it is shrunken to 28 by 28. But you've employed 6 filters, so you're left with 6. And then, you know, after that, if you use 10 filters with 5 by 5 by 6, because you're this is 6, this is 6, and so 6 here comes here, 10 here goes here. And if you apply another 5 by 5 filter, then 28 by 28 will be shrunken into 24 by 24. And you repeat this process until, you know, like it becomes very small. So that is the that was the convolution operation. And also you need to remember what receptive field was. So if you continue applying convolutional operations, and then at the top, so suppose that you are retaining the height and width in this example with padding. So this doesn't shrink, like we're starting with 8 by 8, and one after convolution you're still left with 8 by 8. So suppose that you're using padding, and after you've reached layer 3 here, after 3 convolutions, a fiber, because this is a fiber, because there should be like a gigantic channels here, channels in this direction, a single fiber, like, because this is a fiber, like there's like a long vector like this. So this is a single fiber, or single, like a patch is responsible for a larger patch in the lower layer. So for the input image, this single thing is looking at the entire region here. So we've already talked about this, right? So that's why you want to, and then, yeah. So that's why if you apply attention mechanism on here individually, like here, like if you apply attention mechanism on top of the fibers in certain, you know, hidden layer of your convnet, then you are actually, by attending to this single fiber, that you are actually looking at this entire, like this much, like this much in the input image. So that is why it's a good idea to take the 14 by 14 hidden layers somewhere in the intermediate layers, and then apply attention mechanism, because by using attention mechanism on the hidden feature or the fiber, you are actually you're not actually just looking at one single pixel here. You're actually looking at a patch or region of the image. So what they actually did in the VGG16 is, so VGG16 looks like this. So it has the input layer here, and then you do like they employ a lot of 3 by 3. So before VGNet, architectures like AlexNet, they use like 3 by 3, 5 by 5, 7 by 7. They, like, you know, they mix and match a lot of them. But in the VGG16, they simply use only 3 by 3. And then they just increase the number of layers to increase the size of the receptive field. So given this architecture, they don't take the features from the top penultimate layer right before the prediction. They take the feature from this layer, exactly this layer. So the output of this convolution layer would be 14 by 14 by 512. So that's why I said 14 by 14. So output of this layer is 14 by 14 by 512. And they flatten it. They flatten this to 196, 512. So given this 14 by 14 by 512 image representation tensor, this is a tensor, they flatten it simply like this. So this, if you call this first fiber, if you call this first fiber A1, and if you call the last fiber A196, then if you just flatten it, then this is all you get. So now you are given this as the output of your encoder. If you think about it, in the sequence to sequence with attention, the output of the encoder was similar to this. It was also output of the encoder was like this. So this is like some French word like je suis, whatever, like some French word like French word like da, 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 and then end of sentence. And each word became a hidden layer from the RNN encoder. So this is one hidden layer. So this is H1. This is this layer, this fiber is H2, so on and so forth. Exactly like this. You instead of having, so here the number of fiber was the same as the number of input words, but here you have the number of fibers is fixed to 196. Whatever image you give to the encoder, you'll always end up with number 196 fibers as the output of the encoder. So the rest is the same. The rest is the same manner that you did with the attention mechanism on top of this. You can do the same with attention mechanism on top of this. That's it. Yeah. So this decoder architecture is exactly the same. And you need a context vector every single time you want to predict a word. You need a context vector, and the way you generate a context vector is you based on this 196 fibers. Yeah. So yeah, the high level flow work is each yi is predicted based on, of course, the hidden layer of the RNN, the decoder, and each decoder hidden layer is derived based on previous hidden layer, previous output, and your context vector. And your context vector is derived from your previous hidden layer and your fibers. And of course, there would be, if you look at the details, you mix and match basically. So there's hi minus 1 is fixed, and you just have, so yeah, we're at the time step 2. So what you have is h1, and then you have f attention function h1 a1, f attention function h1 a2, all the way to f attention function h1 a196, and then you do a softmax on top of this, and then you get alpha 1, alpha 2, all the way to alpha 196, which are attention weights. So that's what's happening here. You have a function, attention function. As I said, it's an MLP function with some maybe one or two hidden layers, and it's the input to that function is the previous hidden layer and each individual fibers. Basically, you can concatenate it. Actually, I'm sorry. Yeah, the attention. As I said, the attention module was MLP, but I actually mistakenly copy pasted this matrix multiplication type of attention function, like from the sequence to sequence of attention. What they did is they just had a single weight matrix, and they did this kind of like a matrix multiplication. But in this show, attend, and tell, in this particular paper, they use MLP function, not this function. But in spirit, it kind of doesn't matter. As long as you have as long as your function has enough power to mix these two information together, then it's all good. So the output of this, let's just say we use this instead. So the output of this will be a scalar value between negative infinity to positive infinity. You gather all these scalar values for individual fibers, put this into softmax, and then you get the alpha weights, and then you just do a weighted sum over the fibers with the alpha weights, and then that's how you get the context vector. Then you get the context vector, you concatenate it with your previous output, and then you proceed with the RNN, obtain the H1, and then you get the final softmax output for your next word. Actually, this should have been that one. Yeah. Okay, super easy, right? There's not much. It's almost exactly the same as sequence to sequence with attention mechanism. It's just that the encoder outputs a fixed number of fibers instead of variable number of fibers. The rest is exactly the same. 재균님, 네, 아주 좋은 질문이십니다. 네, 그게 맞는데 저도 왜 이 저자들이 하필이면은 14 by 14를 했는지 잘 모르겠어요. 그게 14 by 14에서 한 파이버가 얼마나 많은 리전을 커버하는지 잘 모르겠는데 엄청 많이 커버할 거거든요. 왜냐면은 지금 하나, 둘, 세 개만 해도 벌써 한 파이버가 이만큼을 차지하는데 지금 이게 하나, 둘, 셋, 넷, 다섯, 여섯, 일곱, 여덟, 아홉 번째잖아요. 그러니까 아홉 번의 컨볼루션을 거쳤는데 그러면 여기서의 리셉티브 필드는 어마어마하게 클 거거든요. 그래서 저도 정확하게 왜 이제 14 by 14를 했는지 잘은 모르겠는데 어쨌든 말씀하신 대로 적당하게 좋은 걸 하는 게 좋습니다. 그리고 이게 또 고려하셔야 될 게 이게 그렇다고 너무 아래에서 놀고 싶으면은 이제 리셉티브 필드가 너무 큰 게 싫다. 나는 좀 적당하게 하고 싶다. 그래서 아래로 가면은 여기서는 이게 14 by 14가 아니라 뭐 예를 들어서 한 20 by 뭐 22 by 22쯤 될 거거든. 뭐 예를 들어서 22 by 22다. 그럼 얘네를 플래튼 하면은 뭐 400 몇 개가 나오거든요. 쭉 해서 22 by 22 곱하기 22개만큼의 파이버가 나오는데 그럼 너무 크거든요, 파이버가. 그러니까 이제 그러면 어텐션 펑션이 잘 안 될 수가 있어요. 너무 크기 때문에. 그래서 지금 적절하게 190력 정도 되니까 이제 또 할만하다 이렇게 될 수도 있거든요. 그래서 네, 뭐 그렇게 뭐 약간 약간 휴리스틱한 접근이 필요합니다. So what Jaegyun Kim asked is very interesting. So what he's yeah, I guess he's a male. So what he asked is, so should we choose the right intermediate layer or output? So should we choose the right intermediate layer to use its output as the encoder output? Because here I said something about the receptive field, the size of the receptive field being, it has to be like an appropriate size receptive field. But here A1, each fiber is looking at quite a large region because after it's been after 1, 2, 3, 4, 5, 6, 7, 8, 9 convolutions. So like just 3 convolutions, it is already looking, a single fiber is already looking at a lot of regions, but after nine convolution, it's probably looking at like a really like entire image, not entire image, but because the entire image is 128 by 128, so it's looking at like a sizable portion of the image. So so that is like something you need to consider when you want to build this kind of like show and attend and tell. But then again, another trade-off is you don't want to go too low to restrict the size of the receptive field, because in the lower layer, the output feature tensor would be higher dimensional. The height and width would be no longer 14 by 14. It would be like 20 by 20 or 25 by 25. And you flatten it, then you will have way more number of fibers compared to flattening 14 by 14. Flattening, for example, 22 by 22 will give you like 400 or 500, whatever. So then you're left with too many fibers. So there's a trade-off, basically. All right, so moving on. So yeah, we've covered everything, hopefully. So, yeah, some details. So actually there are technical details. So RNN's initial hidden layer, which are usually initialized to 0 vector, they didn't do that here. They didn't initialize to 0. They actually initialized initial hidden state is learned. So there's another function. So this is like another MLP that gathers this information. Basically, they just they average out the entire thing. So you're left with 512 vector. Put this into the MLP, and then that'll output the initial hidden state H0. So it's no longer a 0 vector. So when you do backpropagation, this function will also be learned. And authors also, as I said, authors also tried hard attention. So it's no longer like a distribution of like alpha distribution of so no longer a convex weight. So it's just like out of 196 fibers, only one fiber is chosen to predict the word. It's no longer a weighted sum of the fibers. It's just one fiber responsible for generating the next word. And because there's like a hard decision involved, you can't backpropagate it with a hard decision. So you need reinforcement learning on top of it. So this is a bit of a technical detail, so we won't go into detail. But suffice to say that the performance difference between hard and soft is just negligible. So you should just use soft attention. And also they did one more thing, which is to encourage this here. So what this means is the T is the number of time you generated the words. So t is across the time steps. And what this means is that you want your fiber to be used at least once throughout the entire decoding process. That's what this means is. So attention mechanism is sorry. A pure attention mechanism is there's over the I, alpha ti equals 1. So at with a fixed t, like t equals 1 or t equals 2, with a fixed t, attention mechanism forces this behavior, like across like alpha 1 all the way to alpha 196. The sum of it, the sum should be 1. This is enforced by softmax, so this is already preserved. But when you fix the I and iterate over t, I'm sorry, ti 1. What this means is that for a single fiber, it could be a fiber 1 or it could be fiber 196, doesn't matter. You fix a fiber, and then you want that fiber to be attended to at least once over the entire decoding process, so that not a single fiber is left out in the entire decoding process. That's the whole thought process between encouraging this. So basically making the model pay equal attention to every part of image during text generation. Yeah, so this is like there's like another loss term. So there's like a loss term. So there's a single loss term. I mean, the loss term is determined by the negative log likelihood terms. But on top of that, there's like an added loss term, like a regularization term, this one, in the actual implementation of show attendant tail. Okay, so yeah, moving on. So that's the whole technical details. And now you can see that the blue scores compared to the previous NIC, neural image caption, the show and tell. So these are all show and tell. This is not exactly show and tell because this sigma here is indicating that they are using an ensemble approach. So it's like a set of image caption generator and pulling them together for an ensembling. But basically, compared to NIC, there's soft attention. Oh, there's also hard attention. So you can see that the performance difference between hard attention in blue 1 is negligible as it goes to blue 4. And actually, hard attention is a bit better in Flickr 8K. If you go to MS Coco, then it's, the difference between soft and hard, it's not that large. So yeah, in even like another measure, Meteor, soft is outperforming hard. And so I guess, it depends on like the size of the data set and also the quality of the data set. But, in the most frequently used data set, Coco, soft is doing as good as hard. So no need to bother with like, complicated training procedure of hard attention. And also compared to NIC and soft attention, and soft attention is outperforming. Oh, not exactly. In blue 4, actually, no, that was a typo. So it's this one versus this one. Okay, except for blue 4, soft attention is outperforming NIC. So it's probably a good idea to use attention. 그러니까 요게 여기서는 말하는 게 이거는 이제 무조건 1인데, 그러니까 이제 t를 고정시키고 어떤 특정 타임스텝을 고정시킨 다음에 이제 그 알파 1부터 알파 196까지 다 더했을 때 1이 나오는 건 이미 소프트맥스로 이제 고정을 하고 있는데, 이거를 하는 이유는 지금 이거는 i를 고정하고 i를 뭐 예를 들어서 2번 파이버로 고정을 했다. 그때 이제 이게 지금 타임스텝마다, 그러니까 한 번 이걸 디코딩 할 때마다 각기 다른 알파 2가 나오잖아요. 그러니까 이제 한 번 디코딩 할 때마다 어텐션 웨이트들이 계속 생성되기 때문에 이제 한 파이버가 예를 들어서 파이버가 넘버 2다 그럼 한 파이버가 여러 번의 어텐션을 받는단 말이에요. 그러니까 이제 알파 t equals 1, i equal 2, 알파 t equal 2, i equal 2, 알파 t equal 3, I equal E. 뭐 이런 식으로 이제 I를 고정시킨 다음에 이렇게 쭉 돌릴 수가 있는데 이때 이 알파들을 다 더한 게 그러니까 다 sum 한 게 1이 됐으면 좋겠다는 게 대략 1이 됐으면 좋겠다 이거예요. 그러니까 그 말은즉슨 이 파이버 이 2번 파이버가 이 디코딩을 하는 전체 타임 스텝에서 평균적으로 한 번은 쓰였으면 좋겠다는 얘기입니다. 평균적으로 한 번의 이 어텐션을 받았으면 좋겠다는 얘기예요. 적어도. 네네 맞습니다. 네, 다 골고루 받게 하는 겁니다. 네, 그겁니다. 그래서 이 로스 텀을 이제 추가를 해주게 됩니다. 이 실제 이 objective function에 네, 그거예요. Alright, so yeah, some couple examples. Yeah, so there are 6 examples here. So here, this is a given image, and the generated output is a woman is throwing a frisbee in a park. And when it's time to generate or predict word frisbee, it is attending to the frisbee. So yeah, these are all soft attentions basically. And when this image is given, when it's time to predict the word dog, it is actually looking at the dog. When it's time to generate stop, it is looking at the stop. Girl, a group of people, tree, all the regions except for where the giraffe is. Yeah, so it's doing a pretty good job. So yeah, these are the correct attention examples. These are incorrect attention examples. So it's a large white bird standing in the forest. So there is no bird here. It's probably a giraffe, but maybe from far away it looks like a bird. So when it's generating the word bird, it is looking at the giraffe. So that is why it is wrong. So it's kind of like a debugging process. When you have the attention mechanism, it's easier to debug why something is going wrong. A woman is holding a clock. So where did the clock come from? Clock came from this region. A man wearing a hat and a hat. This is also kind of a bug. On a skateboard. So it looks like this is misunderstood as skateboard. This is understood as a surfboard. There's no pizza, but this whole thing is understood as a pizza. There's no cell phone here, but this one is this here is look like a here and here. Yeah, here and here. It's misunderstood as a phone. So yeah, it's kind of a debugger. 네, 하드 텐션 있으면 하얀 부분 크게 동일합니다. 네, 맞습니다. 왜냐하면 한 번에 하나의 파이버만 선택되기 때문에. 그렇죠. 아까 맨 처음에 보여드렸던 그 갈매기 example에서처럼. Yeah. Oh yeah. This is a whole decoding process. Like there's a woman is throwing a frisbee in the park. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. So yeah, 9 procedure plus the dot plus the period. So 10. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, including the dot here. And you can see that a woman. Well, actually. So a woman, so when it was trying to generate A, it was attending to this girl or boy, a girl. But when it comes to time generating woman, it is looking at both things. So I guess it's not exactly doing what it's supposed to be doing because the sentence is a woman, but there are two females, and it is looking at both females when generating woman. So it's kind of like not doing what we wanted to do. Frisbee, yeah, throwing frisbee, all looking at the hand and the frisbee, so it's all good. Time to generate park, it is looking at everywhere except the 2 female characters. Right, yeah, okay, so the last part is text to image. I was planning this session to be only image to text, so image captioning, but then I realized it's a bit a light topic because we've already went heavily through the sequence to sequence. So image to text is a rather easy topic after you've learned sequence to sequence. So I've actually prepared an extra. Question: Does this kind of word tends to have similar attention with previous word? It seems so. There's not a clear way to attend to when you're generating words like words like are or get or or become, is. Those words are hard to ground on the image. Like these words are easy to ground. Like woman, there is actually a woman here, and the frisbee, there is a frisbee. So like nouns are easy to ground on the image, but verbs like some verbs are also easy to ground, like running. Then you just attend to the running person, but is hard to ground on the image. So I'm not sure what the pattern is for like words like these, like is and are. Maybe you're right. Maybe it is just attending to the same part as the previous word. I'm not really sure. Okay, so text to image. So this one is a bit different. So we'll start with an example. So the first, as if I remember correctly, the first work to combine GAN with RNN, basically, because if you want to generate images with text, then you need both components. So the first work is from ICML 2016, Generative Adversarial Text to Image Synthesis. So given a text, which like here, there are two examples. This small bird has a pink breast and crown and black primaries and secondaries. So GAN generated these like 6 samples, 1, 2, 3, 4, 5, 6. And it kind of makes sense. I mean, it looks like a bird on a branch. I mean, if you look at the detail, it is like missing a lot of the details. Like this, there's not exactly a beak. 부리가 없죠 지금 뭐 이런데. But it looks like it's from a distance. It looks like a bird, and it is red, and it has pinkish breast. So and it looks like a small bird. So it is doing something. And the next example is the flower has petals that are bright pinkish purple with white stigma. I'm not sure what stigma is, but at least the petals are purple. So the petals are all purple. And I mean, it looks like it has fallen into mode collapse because they almost look like the identical images, like the same purple flowers, but at least it is generating purple flower. So yeah, it understood something at least. Right. So this is the architecture. I won't go into the equations and all that. It's just probably enough to know the overall procedure and the architecture. And you can easily imagine how you would do this. Like you need an RNN and you need a GAN. So at least you need two components. And so yeah, encode text with RNN, decode image with GAN. So it's, again, you can think of an encoder-decoder architecture, kind of, but due to the training procedure of GAN, where you need a discriminator, not just a generator, you need to inject text information 2 times, one in the generator and another time in the decoder. If there was only the decoder, then it is exactly like encoder-decoder architecture. If you exclude this, and if you look at the generator, then encoder is this part, the RNN, and then you feed this information into the GAN generator, and then this is your decoder, and that's it. But in order to train your GAN, you need a decoder, you need a discriminator network. So you inject your RNN information once again into the discriminator network. So that's the only caveat, and the rest is the same. And of course, when you're generating an image, you need to upsample starting from pure noise, where you sample from like uniform distribution or normal distribution. You need to upsample, and upsample, they use deconvolution, exactly like the ones used in DC-GAN. You've already all used DC-GAN for your project, so you know what DC-GAN is. So in DC-GAN, they use deconvolution, which is like the like inverse or transpose of convolution. So yeah. If you're interested, if you want to know the details of deconvolution, you can just look it up on the internet. I mean, do I have it here? Yeah, I don't have it here. Yeah, there's like a very nice drawings, a lot out there. Just anyway, so yeah, 디스크리미터는 그림과 문장을 동시에 판단해야 됩니다. 그래서 문장을 넣어주는 거예요, 그림과 같이. So, all right. So the architecture is you need random noise from the normal distribution, and then you concatenate that noise along with the RNN output. So RNN output. So here, which would be the final hidden vector of your RNN encoder. So it's probably whether it's LSTM or GRU, doesn't matter. You encode, you input you feed your sentence into the RNN. You get the final vector, HT or HN or whatever, like the final hidden layer. You take that and then concatenate it with the random noise here, right? And then you start from here, start deconvolute, start upsampling, and then generate a certain image. And then given this image, you contract it using a convnet into a hidden tensor, and then you take the output of the encoder, the same encoder, the last hidden layer, HT. So let's say that here you take this one. This is like, let's say this is 10 by 10 by 512 or whatever. So this portion, your image hidden tensor is 10 by 10 by 512, and then you take your hidden layer from your RNN encoder, and then that would be, of course, that will be just a 1 by 1 by some hidden dimension. Let's just say, for the sake of argument, this happened to be 512. So you're using 512 dimensional RNN. Then what you do is you copy this 100 times, because you need 10. This is 100. There are 100 fibers, right? So you copy this 100 times, and then copy this 100 times to make this into 10 by 10 again. And then you concatenate here by here. So you concatenate your image hidden vector with your copy pasted RNN hidden vector. Then you contract it some more times, and then you finally generate like 1 or 0, being like real or fake. So that's how both image and text information is given to the discriminator. G와 D 모두 인코더와 디코더 가졌다고 말하네. 아니죠. 네. 인코더는 여기선 사실 이거 RNN밖에 없습니다. 여기가 디코더고, 이건 이제 학습 때 필요한 디스크리미네이터인데, 디스크리미네이터에서는 이 RNN의 그 정보가 다시 한번 흘러 들어간다는 거죠. 왜냐하면은 그림이 맞았는데 이게 틀렸을 수도 있잖아요. 이거 그림은 꽃을 줬는데 뭐 새에 대한 이야기를 하고 있으면 당연히 페이크라고 0을 뱉어야 되니까, 이제 그런 걸 학습하기 위해서 이제 여기에 이미지뿐만 아니라 텍스트도 같이 넣어주는 겁니다. 지수님, so in this case is the role of the discriminator checking if the text to image translation is done correctly, instead of simply deciding if the image is fake or not. Exactly that. Yes, exactly. So it needs to look at both the image and text to decide whether those two sorts of information, that pair is correct pair or not. So not just that the image needs to look like real image, but the text description must be also a corresponding description of the image. So that's the that's the text to image. So the training procedure is a bit complicated compared to just simple GAN, because there are 4 cases. Discriminator's job is complicated. It's not just fake or real. Discriminator job is divided into 4 cases. So is it real image with right text? Then it should be real. Fake image with right text, it should be fake. So fake image being like, not a realistic image, like, some just, very low quality image with right text, then it should be fake. And it's the high quality image with wrong text, is still a fake, because the text description is mismatching to the given image. Bad image with wrong text, obviously a fake. So there are 4 cases. So in order to train the discriminator properly, the authors of this paper used these 3 cases: real image, right text; real image with wrong text; fake image with right text. So they don't actually do this because this is too obvious. If the image is fake to begin with, then the discriminator job is too easy. So they don't need to actually consider this. I mean, that's just why, in my estimation, why they decided not to include the 4th case, because it's too easy. But yeah, these 3 cases. So they, if you look at the algorithm for training the conditional again here. First, they encode the matching text. So the right text and wrong text are encoded. So there's H and H hat, which are the right text representation vector and the wrong text representation vector. And then they have three cases here, three cases. Real image, right text, real image, wrong text, fake image with right text. And then they give this to the discriminator. So the total discriminator loss is like this. So loss from real image right text, loss from real image wrong text, loss from fake image and right text, because this should be the only one, and these should be 0 for the discriminator. And these two are summed up and divided by half. So, just to balance things, right? So, because you don't want one, and 2 zeros. You want the ratio to be like approximately the same. So the two losses are halved into 2. So that's the loss for the discriminator. The loss for the generators, there's only one loss. It's this one, fake image with right text. So fake image being like synthetic image. So for the generator wants to fool the discriminator with the synthetic image with the right text. So this is the only relevant loss for the generator. So that's it. LD and LG. That's the whole loss function for the GAN, the text condition GAN. Some examples. Yeah. By the way, these are all like 0 shots. So the image, the GAN has never seen a text like this, nor the image like this, So these are different variants of the GAN. So basically, it's just like different ablation study. So given this text, an old black bird with a distinct thick rounded bill. I think bill is like puri, or beak is, I'm not really sure. So anyway, so yeah, look at this, and these are at least all blackbirds. Looks like a blackbird, and the background is pretty varied, so it didn't fall into the mode collapse. This looks like a mode collapse. This is pretty there's diverse set of examples, and these are all like bird. So there's like a San Diego bird dataset or something. So it's a dataset of bird and its description. So they use that dataset to train their GAN, and this small bird has yellow breast, brown crown, and black superciliary. Yeah, I'm not sure what that is, but at least these birds all have yellow breasts and brown crown. Crown here. I'm not really sure. Anyway, yeah. This is like all poor images. This starts to look good. This one's like pretty good. Yeah. Maybe the last one. The gray bird has a light gray head and a gray webbed feet. So yeah. So webbed feet, gray, whatever. Yeah. So gray head, gray bird. And if you go to the bottom, it doesn't look that gray to me. Maybe they look like seagulls. So maybe this model has seen a lot of seagulls. So that's why it's trying to imagine a seagull, because as I said, these are all 0 shots. So the GAN model has not seen this nor this text during training. So anyway, so the resolution is not that good, and also the details are all missing. I'm not sure. This is not a complete bird, nor is this. It looks like it has the form of a bird, but it's not exactly a complete bird. But still, it is generating something that looks like a bird. If you go, these are all like the flower examples. I'll just skip this. Yeah, so this is the last one. So this is a bit more diverse topic. So I think this is MS Coco, maybe. These are all, so these were all bird data set. This was all a flower data set. This is a bit more, like it has more objects. There's like people, like food, or like objects in the tables. So if you look at this one, the GT is a table with many plates of food and drinks. So there are a lot of objects. It's not just one bird or one flower. It's just like plates and tables and cups and juice. And what the model generated is this. Yeah, this doesn't look that good. Maybe this one. A group of people on skis stand on the snow. So yeah, this does look like people on the snow plane. This as well. Yeah. Looks like a ski resort to me. Yeah, maybe the baseball. So a pitcher is about to throw the ball to the batter. Yeah, so there's a lot of artifact. Yeah, this is not a person, nor is this, nor is this, but still, like if you look from the far away, it looks like a baseball, I forgot, like a ground or a field. Yeah, baseball field. Looks like a baseball field. This looks like a baseball field, and there's like a couple of people and maybe an umpire, the crowd. So it kind of understands what it wants to generate. It's not, but the problem is not the details are all kind of missing. So the the model is probably underfitting. So you need like a bigger model, like gigantic model compared to just. I'm not sure what kind of architecture they use, but they could probably grow the size of the model to get a better like image quality. 로스에 -1 있어야 되는 거 아닌가요? 네, 뭐 로스니까, 네, 네, 아마 그레디언트 디센트 때문에 이제 이걸 마이너스가 돼야지 줘야 되는, 네. 10을 맥시마이즈 하는 건가요? 네, 그러니까 이거는 지금 다 디코더가 디스크리미네이터가 맞는 경우에 지금 이건 디스크리미네이터가 이제 1이 돼야 된다. 얘는 지금 -1이니까 이제 이게 0이 돼야 된다. 0이 돼야 된다니까 디스크리미네이터가 이제 맥시마이즈 해야 되는 밸류거든요. 그러니까 이제 이거는 디스크리미네이터가 맥시마이즈 되는 밸류. 이건 이제 제너레이터가 맥시마이즈 해야 되는 밸류인데 이제 실제로는 이제 이거를 그레디언트 디센트로 미니마이즈 할 거니까 뭐 당연히 이제 그거에 맞게 적절하게 이제 뭐 플러스 마이너스를 취해줘야겠죠. 네. 네, 그렇습니다. 네. Okay, yeah, that's the end of the examples. So yeah, that's the end of class. So yeah, okay, it's already 12 o'clock. So yeah, I was hoping that we would end early because of the the topics were already quite familiar to begin with, but again, we took a long time. So all right, this is the end of the class. If you have any questions, I can actually stick around a few more minutes. 질문 있으신가요? 오랜만에 일찍 끝나니까 조금 시간이 있는데 뭐 일찍도 아니죠. 뭐 12시에 끝났으니까. 네, 프랙티스 세션 때는 이제 플리커 AK로 show attend and tell을 한번 이제 구현을 해볼 겁니다. 이미 시퀀스 attention 하셨기 때문에 별로 어려울 거라고 생각하지 않아요. Right. Yeah, I just said that during your practice sessions, you guys will be implementing show attend and tell, which is exactly like sequence with attention. You just replace the encoder, RNN encoder, with the image encoder, and that's it. All right, if there are no more questions, then we'll just end the class today. I'll see you guys this Thursday. All right, thank you guys. Bye-bye.